All right, I think we're good to go. Hello, everyone. Okay, I can probably look at some problems at the end, but I'm just gonna lecture for like an hour, I guess. Usually I do the problems on Wednesday, but I guess I can start doing problems at the end of Tuesday and Friday as well. Um, I just have to warn everyone, I did throw out my back a little bit, so I might just like go into some pain randomly. It hurts kind of bad. Hold on, I gotta adjust this. Yeah, I don't know how I hurt my back this morning, but it hurts like right over here. But okay, I think we're good to begin. Okay, so last time we were talking about this asset pricing model, where essentially in the one period model it can just change by going up or down by some up factor or down factor, which we call U or D. Pain amuses me. Yeah, I wish it amused me. This one hurts. But also, I realized I made a mistake in this example that I was doing at the end on Tuesday, I think. I wrote the reciprocal by accident in my notes, and I just didn't really think about it. Also, I believe this number always has to be less than 1, so that's another reason I knew I had the wrong answer, because I think I wrote 70 over 40. Somebody can correct me if that's wrong, but so I just wanted to correct that, and also going over this example again will make the multi-period stuff make a little more sense. So yeah, that's basically where I'm going to begin. And yeah, I just wanted to remind people that I do tutoring in, any subjects that people might need, calculus, any algebra subject, linear algebra, probability. I know most people are probably not taking classes on this in particular, but if anybody wants to brush up on their financial math or any type of anything related to this, you can also contact me. So yeah, so the multi-period is just going to be basically an extension of this, and we'll write down a theorem in a second that will basically codify what we're doing in this one period model, and it'll basically be a recursion where we go back. If it's multi-period, everything we're doing in the one period model, we're just going to repeat this over and over again. It's going to be like this recursive process. And at each point, the option or the derivative or whatever the thing that we're trying to replicate the portfolio of, there's going to be some delta delta I at that at that point in time. So for the one period model, there's just delta 0, and that's basically saying how much of the stock should I buy that is going to replicate the portfolio for some option that has some payoff. So for the yesterday one, we had a strike of 110, and if the stock was at 150, it had a payoff of 40, because we just take 110 minus the strike price. Or if it went to $80, then the option was worthless. It was basically worth 0, because 80 minus 110 is negative. Right. So yeah, and then this is just kind of like we picked an interest rate here. I just said it was like 5% per year. All right, so are there any questions about the problem last time? And then I just have this correction where I flipped this fraction by accident. So in the one period model, we said that the amount, so we had maybe there was some 50% odds in real life that this stock was going to go up and 50% that it was going to go down. But we said that there was some change, basically like change of measure, where we if we viewed the probabilities differently, then this was like a risk-free measure where on average the stock would be going up the risk-free rate, which was this 5%. And remember, there's this change of measure idea where we forget about the real percentages that it might go up or down, and we take on this new idea, the new probabilities. Remember, because when we price the option, it doesn't really matter what the actual chance that the stock goes up or down is. Yeah, and you can kind of see that here because this 50% probability doesn't play a role in the this P tilde or Q tilde here. It just depends on R, D, and U. Okay. Yeah, so was there anything else I wanted to say more about this? And then, so basically we could calculate the price of the option as the discounted by the risk-free rate amount. But with this, considering these probabilities, we could consider the option as the weighted average of the payoff values, so of 40 and 0, but weighted with these risk-free probabilities, so not the 50-50. So I guess if we wanted to draw the other one, the other binary tree for the payoff for the option, it would basically, I guess I can just erase this for now. So the stock goes from 100, it can go up to 150 or down to 80, but the option can either go to 40 or 0. And the option is going to have some value, which is, maybe I'll put it in quotations here, P hat. We're going to think of it as having these probabilities, the ones we calculated over here. And so it has like P hat chance of going up and being worth $40, or Q hat chance of going down and being worth $0 in the risk-free measure. And if we think on average it will give us the risk-free rate, then there's a way we can calculate V0. It had a formula. It was like 1 over 1 plus R, and then probably not enough room here. So P hat V1 of H, which was like the up value. I really just don't give myself enough room here. Okay. Can everyone see this? So it's basically 1 over 1 plus R, and then times P hat times the value of the option if it goes up, which we could think of as like flipping a coin and the coin flips heads, or plus Q hat times V1 of T, which was, the value of the option if the stock goes down, it was worthless. And then, yeah, the discounting just has to do with the fact that we expect on average in the risk-free measure that if we're not taking any risk, we should be getting the payoff on average of the risk-free rate, which is the 5%. Okay, so that's basically the idea that we went over at the end of last time. I just had flipped this fraction by accident. And how did we calculate this delta at each point? The delta was just the difference of the option prices, the difference that it could possibly take for the two different values, divided by the difference of the stock values if it gets heads or tails. So basically the formula for this was V1 of H minus V1 of T divided by V1, or divided by S1 of H minus S1 of T. So V1 of H minus V1 of T over S1 of H minus S1 of T. Like that. And that gave us 40 over 70 because it was, 40 minus 0 divided by, I think it was, 150 minus 80, right? So 70. Okay. So that was the example. And this delta is very important. This is like if you take finance or if you work at a hedge fund or something, this would be like the delta of the position or the this is what you would have to hedge if you were short the option. It's kind of like this is like the equivalent of how much stock you would have to buy to equal the position that buying the option would be. So if you buy this option, it's almost equivalent to as if you bought like 0.57 shares of the stock. Except the interesting thing about this delta is that over time, as the stock goes up and down, the delta actually changes. So there's actually like you can think of there's like a derivative to the delta that the delta actually depends on the time. If you think in the multi-period case, this delta is going to be changing over time, and then it could be going up, it could be going down depending on the stock price, the time, and if you have more complicated models, it could also depend on like volatility or a bunch of other stuff basically. Okay, so any questions about any of this for the single period? And then the multi-period one is, like I said, you're basically going to be doing this, but you're going to be taking these averages, and then you're going to keep doing this over and over again, and you're going to get a bunch of values that are defined recursively. Okay, so I think, yeah, that was the example from last time. Do you have any questions about this, Jeff? Actual education dad? I'm not sure if you're interested in this math, but... So yeah, and then I think Mavort had asked me at the end. I kind of ran out of time. I had to go, but was asking about the replicating portfolio, and the replicating portfolio just says how can I trade in cash and the stock to basically replicate the price of this option as the way we calculated it here. So the theorem I'm about to write in a second says that there's basically a way to pick these deltas all the time. And if you adjust it at every time period, there should be a way to replicate the price of the option. So essentially, you can just keep buying stock. If the stock maybe if the stock goes up, you buy more stock depending on what the calculation is for the delta, or maybe you sell more. It just depends on what this is. So yeah, let's look at this replicating portfolio theorem, and I think that should answer the question from the end of last time. Okay, no questions? Okay, right. All right, let's just jump straight into the theorem. So this is, again, this is a book by Shreve. I believe that's Shreve. And the book is Binomial. I think it's Binomial Options. What's the name of the book again? Have it right here. Oh no, it's Stochastic Calculus for Finance 1. That's easier. Yeah. But honestly, I wouldn't even really call it stochastic calculus at this point. I would say it's more like an introduction to stochastic calculus, because really everything we're doing here is just finite models, so nothing too crazy is going on. But maybe I'm wrong about the terminology. Maybe it makes complete sense, I'm not sure. So this is theorem 1.2.2. And this talks about replicating in the multi-period binomial model. So we're going to take the single model that we just did and basically repeat the process like I was talking about. So when we say replicating, what I'm saying here is that, again, remember I was saying that we could replicate the payoff of the option by just buying or selling some amount of the stock at every period based on this delta that we can calculate. So the full theorem, which will look very similar to what I just erased. So again, this says that we can define this p hat this way, same way as before, so 1 plus r minus d over u minus d. And then q tilde is 1 minus p tilde, of course. And then it says the price of the option at time n given the first n coin flips, meaning that, you know, each coin flip is either heads or tails, either the stock goes up or down at each point, so this is either like H or T. Any Ito calculus here? No, that's why I was saying it's basically not really stochastic calculus yet. This is kind of like, this is like discrete stochastic calculus, if you want to think of it like that. So the Ito calculus stuff doesn't come in until you go into the continuous version of this. But this is very powerful stuff, and you could think of this as like how do you say that word? Discretized version of the continuous version. So there is like some Ito stuff going on, but it's kind of like approximately Ito, if that makes any sense. Like in the limit, you'll have like these Ito relationships with the stochastic derivative and stuff. So this theorem is saying that the price of the option at time n, given the first n, ups or downs of the stock, is basically, again, it's 1 over 1 plus r, so we're going to discount by the risk-free rate, and then it's going to be this average in the risk-neutral measure, so p hat, or p tilde, Vn plus 1, all the same omegas, and then it's going to go heads at the end, plus q tilde Vn plus 1, same thing, and then tails. So this was basically the same formula we had before, except we didn't have all these omegas or w's or whatever you want to call these. But this is just saying that the price of the option at time n is determined. It's a weighted sum. It's an average in this measure of the values at n plus 1 based on whether if it goes up or if it goes down, the heads or the tails. Okay, so that's for Vn, and then we also have a formula for delta n, which says how much of the stock we should buy, or how much position that this option is essentially equivalent to in terms of like number of shares of stock. And this is, same formula. We're just going to take the difference of the Vn plus 1s divided by the difference of the Sn plus 1s, the price of the stock. So it's the actually, yeah, I don't need to write in all the, I guess I'll write it in, but there's technically all these W's here. Yeah, so this is Vn plus 1, all the W's, and then heads. Oh, I'm running out of, yeah, this is really annoying. All right, I'm just gonna write, instead of all those W's, I'm just gonna write 1 omega at the beginning. But this basically just represents all of these. So it's all of these, and then I have a heads, like the stock goes up. Whatever we were at here, then it goes up. So a head. And then the same thing, but tails. And then, yeah, similarly, but for the difference between the stock prices. So stock at n plus 1, omega is then h, minus stock at n plus 1, omegas, and then tails. Okay, so very similar formula as the one period model, except, you know, this is just defining it at a certain position. So once we've had a certain number of ups and downs, this is a certain position on this like multi-period binomial tree where, you know, at every point the stock can either go up or down by some percentage. And since it's multi-period, you know, it could go up a bunch of times and then go down a bunch of times. And so this model just says if I pick a point on the tree, I can always figure out what the value of the stock should be at that point, or the value of the option based on the prices of the option at the next event, the next period. So this formula actually lets you work backwards because you can define all the option values at time n based on n plus 1, and so then you can go backwards 1 and you can keep going. And it also tells you what the equivalent amount of stock would be that you would have to buy that would basically be equivalent to owning the option at that time. Right. So in the continuous version, this would be like your delta. This would be like the derivative of the price of the option with respect to the stock price. So you can kind of see this almost looks like a derivative because it's like a difference. You can kind of think of this as like the derivative of the stock price with respect to time, and then this is the derivative with of the stock price, of the option price with respect to time, and then the stock price with respect to time. And this is some sort of like chain rule where you're losing the divided by the difference of time, and you just end up with like difference of the option price, difference of the stock price, and so here I'll put it in parentheses, but this is sort of like if you take the limit in the continuous version, this is like a derivative, like a stochastic derivative, which is like the derivative of the price of the stock divided by the derivative of the price of derivative of the price of the option divided by the derivative of the price, or the differential of the price of the stock. So this is sort of playing like the role in the continuous version that this like DC DS thing would play for the stochastic calculus stuff that I guess the Finance 2 talks a lot more about this stuff. So basically we haven't gotten there yet, but yeah, this delta is very important. This is like your hedging delta, your the delta of the option. And then if anyone's interested in this finance stuff, does anybody know what the derivative of this with respect to the stock price is? So you have like the delta. How is the delta changing with respect to the stock price? What is that usually called in finance? Does anybody know? So this is like the delta. I guess they all have like Greek letters, right? So yeah, this is like delta, I believe. I think there's like 6 of them, if I'm not mistaken, but delta is usually the most common. There's another really common, I guess they call them the Greeks in finance. So yeah, to answer your question, Zone Ranger, yeah, a little bit of stochastic calculus going on here, but only if you take like the limit and go and look at this in the continuous case. Then in the continuous case, you have like these stochastic derivatives, and this would like turn into one of them, which would be this derivative of the option with respect to stock price. Okay. Guess no questions? So yeah, the theorem essentially says that at every point in time, if you just adjust your portfolio to have this amount of stock, and you start out with the V0 amount, so if you set your starting like cash to be X0, which is equal to V0, then the theorem says that at every point in time, if you just buy delta N worth of stock, and you keep adjusting your portfolio at every point in time, then you should be able to replicate the payoff of the option. So at every point in time, if your portfolio value is the xn and the option value is y, vn here, if you keep readjusting your portfolio to have delta n stock at every point in time, then you should be able to replicate your portfolio xn should be equal to vn for every n. So that's what this theorem says. That you can replicate, you can replicate this option payout with a portfolio xn as long as you just keep adjusting your portfolio to have delta n amount of stock at every point in time. And this is, so that's why they call this like a hedge, because if you sell short the option and then you buy this amount of stock, then it should just cancel out all the risk, because if the stock price moves up, then your option should move up about delta n per unit of the stock price, but also your option, the option that you sold short, should also be going up that amount. So, yeah, it would just basically cancel, and then okay. Yeah, so I'll erase this. I will erase this in a second. But, yeah. So essentially, like I was saying, everything comes down to this delta n. So I'll write a little bit more intuition for that in a second. Yeah, no, we haven't gotten to shorting yet. I guess we could talk about put options, but all I've done is call options so far, Pen. Yeah, no, we'll be writing options on different channels, stocks. First, we all have to come up with different cryptocurrencies, right? And then just kidding. Just kidding. Yeah, I thought I'd change it up a little bit. I feel like most people probably haven't seen a lot of this stuff, and it's not really commonly taught in any like undergrad classes for sure. Like, at least as far as I know, I've never seen it. Pencoin, yeah. Okay, yeah. So what I wanted to say here real quick before going on was, in my notes I just wrote general idea for options in terms of this delta. And this isn't really in the Shreve book. This is kind of just my understanding of it that I've come to over time, which is that for options, again, remember you have this sort of convex payoff curve where, whatever the strike price is, strike, if the stock ends up below that, right? Let's see, let me label my axes properly. Yeah, so this x-axis would be like the stock price increasing, S. And then this would be the payoff. So you can see if the stock price ends up below, like this would be K, I guess, then you just end up with a payoff of 0. And if the stock price is above K, then you just end up with this like linear payoff. So overall, it's not linear because this kind of gives you this convexity overall, the fact that it's paying off 0. And you know, your intuition here is that this is a very nice payoff structure to have because there's very little downside risk. The worst case scenario is that this thing is just worthless, but it could end up being worth a lot. So, you know, depending on how much the stock goes up and whenever the option's, you know, not worth anything at that, or whenever the option is expiring. So yeah, because of this convexity, what this means in practice for this multi-period model is that this delta n. So for a call, let's do a call option, I guess. So for a call option, this basically means that when the stock goes up and down, we're going to be essentially buying it as it's going up and essentially like adding on to the increase in the stock. You'll be buying it when it's going up and then selling it when it goes down to kind of, you're really thinking of the derivative of this curve here, which is like this theoretical value of the option here. The curve is like delta. This is like your dCds I was talking about. In the for the continuous version, this would be what's going on. And you can see that there's like this convexity here. So this line, if I follow it down here, it actually goes lower, and that means we're basically we would be selling some of the stock when it goes down and buying some when it goes up. So there's this, you know, second derivative is positive. So for a call option, this means that this means that we're buying stock for the replicating portfolio. We're buying stock when it goes up, and selling it when it goes down. And how much are we buying and selling? Well, it depends on that delta that I just erased, whatever the formula tells us to. For that delta n that I just erased. Academy of Useless Ideas. Hey, Penn, have you missed me with the fiery intensity of 1,000 white suns? So yeah, I hope this is clear to everyone. So call option, you have this delta n that you're calculating, and in general, when the stock goes up, at least for European options, maybe there's like some tricky payoffs or some weird situations you could come up with. This is not true, but at least for the simplest European options, simple payout, just some time to expiry. When the stock's going up, this derivative is basically increasing, which you can think of the delta as the delta. And when the stock price is going down, the delta is decreasing and you're selling some of the stock in for the replicating portfolio. You would be selling stock. So you can think of the replicating portfolio and the option as essentially equivalent if you could actually, you know, trade really quickly every period. Also, you know, we're making a bunch of assumptions here as well, which is like the stock could only get those two values or you know, those range of values at every point in the period. So that's another assumption, which is not exactly true, right? Because the stock could potentially take on any value. It doesn't need to just take on those discrete values. But if you kind of ignore that and use your imagination a little bit and you just pretend like we're working in the continuous case, then you could see how this would be true, where the delta for an option. So you can think of this option as essentially being like this convexity of trading, where stock goes up, I buy more, and then if it keeps going up, I make even more money than if I had just had the same amount of stock the whole time. And if the stock goes down, if it starts going down, I start selling stock, and I kind of like lower my losses because, you know, as the stock goes down, I'm selling some of it. I don't get it impacted as much by the losses. So that's what you want to think of in terms of convexity. And an option basically just buys you this convexity where you're buying stock when it goes up and selling when it goes down. Question also applies to you. I noticed that in your browser, your icon is a little too gray, so it is not so obvious that you're actually streaming. Maybe some more colorful design would help me know when you're on. Might just be my issue, though. What do you mean in the browser? My browser, your icon? Oh, the icon is a little too gray. Okay. I'll think about that. Which icon do you mean? The one on Twitch? Thinking about what you mean. The browser. Are you talking about on the left part, like on the Twitch banner? I'll take a look at it. Yeah, thanks. Okay. So yeah, and then a put option is similar, except put option you're making money when the stock goes down, so it would be similar, except when the stock is going down, you're selling you're selling more stock short, and then when it goes back up, you're buying it back. So basically the opposite of this. It's the one on Twitch. Yeah, I'll take a look at it. Color, the icon becomes more colorful. Okay, yeah, I'm not sure. I'm still trying to figure out everything on Twitch. I've been here for like a couple of months, but I mean, Rex is helping me out on a lot of stuff, but even then there's a lot of stuff I don't know how to do, so I know I'm dependent on a lot of my chatters, so I appreciate that. Okay. So hopefully this makes some sense. There's also some weird stuff you could do here where you can have the payoff be some like weird type of option or just some like function of the stock price. It could just be like the square root of the stock price, or you could, this is just one particular payoff. The cool thing about this multi-period stuff is you can actually change the payoff function, and you can still calculate these deltas the same way. Nothing really changes, and you can basically create your own type of option, and you have a formula now for the replicating portfolio. You just have to basically adjust by this delta n every time. So kind of cool, you can use the same exact math to not only replicate a call option, but a put option, and then really just any type of payoff function we could possibly imagine, which, there's a lot of those, so it's kind of cool. We just basically went through all the same math to do all of these uncountably. I guess you could think of it as, if we want to get really nerdy about it, right? There's uncountably many payoff functions, right? And we did all the math for all of them, right? We can essentially replicate a portfolio with cash and stock that replicates any payoff function. We just need to calculate the same delta n, which was like, Vn plus 1 of getting heads minus Vn plus 1 of getting tails, and then same with the stock price. So if we pick any payoff function at the end, as long as we calculate these delta n's, we can replicate a portfolio. That's what the last theorem was just saying. Okay, so what would happen? I kind of came up with an interesting question / example, I guess you could say. I guess it's a little bit of both. And I guess I'll write it on the board, and then I'll ask you guys to think about it for like a minute or so. But what do you think would happen if we had a situation where, let's say we have a stock and a call option? So the question is, what happens in this situation? Let's say we start with the call option at time 0. There's some delta 0, and let's say the stock just keeps going up and down. So there's like some delta 1 of H. And let's say when it goes up and then down, it ends up at the same price. So there's also some like S0 here in the background, S1, S2 here, but S2 is equal to S0. So delta 2 heads, tails. And let's just say it keeps doing this forever. Or not forever, but let's just say it does this like 10 times. So every time the stock price goes up, then the stock price goes down to the same price it was originally, then it goes back up by the same percentage, then it goes back down to the same amount. And let's say it does this like 10 times, so there's like a delta 1, delta 2, delta 3, delta 4, delta 5, all the way up to delta 10. So the question is, well, the first question I have is, what happens with, what is happening with the delta i's? And then also, what's happening with the stock price? Well, actually, no, 3 questions. Well, we know what's happening with the stock price. The stock price is not going up or down. It's just, staying the same. Maybe it's going up slightly, but it ends up the same every other period. But what's happening to the price of the option, this theoretical call option? We don't even care about the strike. It could be any strike. So what happens with the price of the option, which would be like VI? So there's like some V0 here at time 0. Then the stock goes up. There's some V1H, the price of the option, given that we had the stock price go up. Then the stock price goes back down. The price of the option goes back down. No, same thing. So I guess the question I'm really trying to ask is, we know that the stock price is staying the same each time, but what's happening to the price of the option? So we have the price of the option, it might go up, then it goes down, then it goes back up. So yeah, I'll let you guys, if anybody has any insights on either one of these, I'd be interested in what you have to say. But yeah, this was just something I was thinking about. Can everyone see that? Yeah, it will be converging to the payoff, but yeah, I mean, it would be converging to the payoff of, depending on where it ends up on the final one, it would be, you're correct that it would be converging to the payoff of like whatever the payoff of the option was for this S0, right? Because the stock price at the end would be the same, or at least close to the stock price at the beginning. So you're correct about that. Not exactly what I was looking for, but technically you are correct. That is what it is doing, yeah. But the VIs, yeah. So actually, yeah, the VIs are converging to that. Yeah, that's correct. So yeah, that's actually a good point, Slim, right? What if the payoff at that point is 0 though? So what if the payoff here, like what if the strike price is bigger? Let's assume that the strike price is actually bigger than the initial price of the stock. And let's say at the final one it ends up at S0, because it just keeps going up, down, up, down, up, down, ends up at S0. But the strike price is bigger than S0, so the payoff would be 0, right? But the initial value of the option is probably not 0, right? In fact, I think theoretically for all of these, it'll never be exactly 0. It could be very small, but because there's always going to be some value in the option, because the stock could always end up going above the strike price, right? So it has to be worth something, right? So yes, usually traders will think whether the option is in the money or out of the money. Yeah. So the idea is that with more time, there's more chances that the option will recover. Exactly. Yeah, and we call that like the theta of the option, which is like the time decay or the time value of the option. So usually the option, if you have some non-zero volatility in the stock, the option is going to have some value here, even if in the end the payoff is zero or small. So what's really going on here, what I wanted to point out with question 1, is that these deltas are going to be increasing when the stock goes up, which essentially means I'm buying stock, but then when the stock goes down, it means I'm selling again. So I'm buying at a higher price, and then I'm selling at a lower price. I'm actually continuously losing money if I keep doing that over and over and over, because I'm buying stock, and then it goes down, and I sell it at a lower price, then I buy it back at a higher price, sell it at a lower price, and that's essentially where all of your theta is coming from. Because if you wanted to replicate this option, you'd have to be continuously buying and selling stock at essentially the wrong times, and you would be losing money if the stock never goes anywhere, basically. So I guess the answer for one I was looking for is that the deltas are going to go up when the stock goes up. You're going to be buying stock, and then the deltas will go down, and you'll be selling stock. And essentially, if you keep doing this over and over, you're going to lose money in the long run. So this is, I'll just write it here, like theta decay. Or you could think of this as like replicating some realized theta decay or something. I don't know how you want to think of this. The idea is, yeah, okay, I already read that. Okay, so does anyone have anything else to say about this? I think Slim, everything you're saying is like spot on. That's exactly what's going on. There's some time value to this option where it might be worth nothing at the end of this up-down cycle, but at the beginning it has some value to it because of the possibility that it might be worth something. If the stock takes off and flies up way above the strike price, then it will be worth something. And if you have a higher volatility stock, the chance that happens is even higher. Okay, so basically you have this and the delta changing over time based on the stock price changing. We usually call that the gamma. I forget the symbol. Did they just use the uppercase gamma? Or is that gamma? Maybe somebody will correct me, but there's the delta of the stock, and then the gamma is like the derivative of delta with respect to the stock price. And that's always positive for calls and puts. And you can see that here because the delta is like going up when the stock price goes up, and it's going down when the stock price goes down. So either way, it's positive. Okay, and then what happens with the VIs? That's what we were saying, basically. The VIs, which is the price of the option over time, is going to decay. If the stock price never goes anywhere, there's going to be decay. Yeah. Which just essentially means, like when we were looking at this payoff graph before, when I draw the dotted lines, that's like the value of the option now, and this is like the payoff at the end of the option, and the decay is just the fact that if the option keeps going nowhere, that it's going to decay in value down to the payoff and be, either worthless or at least worth less than whatever the value of the option is now. But it, like we were saying, it still has this chance where, if the value of the stock price at the end ends up here, it still will be worth more at that time, at that expiry date. But if the stock never goes anywhere, then it's just going to decay and lose value. And that has to do with this delta is going up and down, essentially. Right. Any questions? I think I'm gonna end soon. I don't really have much else to say. I don't know where should I go with this next time? Should we go into more of the continuous version of this, where we actually get into like some Ito calculus type stuff, and then geometric Brownian motion, perhaps? Yeah, I think that's probably where I'll take this next time. So essentially, we've done the multi-period model now. It's very much like the one-period model, and then the continuous version is just like a slightly more formal version of what's going on here. But then, yeah, we'll have this limiting process, which we'll call geometric Brownian motion, which is very similar to the multi-period model, except, you know, there's no discrete period time. There's just, you know, every point in time the stock is either going up or down, but it's going up or down by like some infinitesimal amount. And then, yeah, there's a way to measure, like, you know, how much volatility it has on some infinitely small scale, you could think of it as, and stuff like that. Got a comment here. You can, for example, draw that curve for different times, and the curve will converge to the payoff. Right, yeah. Yeah, exactly. Yeah. That's a good way to put it. Yeah. There's like this curve. That's sort of what I was trying to imply here. So like maybe if there's more time to expiry, there's going to be more premium here. You're going to be farther away from the payoff, and this curve will, in some sense, be like smoother, and it'll look more like a, you know, analytic curve, like very smooth. As the time to expiry gets closer and closer to, you know, the option expiring, it's going to go from looking like this to maybe like this blue intermediate line, and then very close to expiry, it's going to be very close to this line, and it's going to be a sharp turn here where the derivative is actually going to change is going to change a lot if you're near this point at the end, because you have a very high curvature point here. And you'll see this at the end of an options life cycle. If the stock is very close to the strike price at the end, you'll get these wild swings in prices, because it's going from basically being worthless to being worth a lot. And, you know, you can go from a number that's very close to zero to a number that's very high, and this return could be extreme. So yeah, Slim makes a good point. There's basically like this whole cascade layer of these dotted lines based on how close you are to expiry, and they kind of converge to this payoff curve. Yeah, and you can basically make any payoff curve, but this is the one for a call option. And you can also make payoff curves that are actually concave. So this is only, I want to stress that this is just one particular example, and it just happens to be convex. You could make weird payoff curves that are like neither convex or concave, but yeah, I mean, yeah. Basically, for financial engineering purposes, it basically just matters, is it concave, is it convex? You could make these more complicated ones where you have like, you know, butterflies or whatever the other weird ones are, but yeah, they're all kind of just combinations of these ones. All right. Does anyone want to go over? Oh, if the option. Let's see. Another comment. If the option is in the money in a continuous model, the gamma will blow up. Yeah, that's exactly what I was just talking about. That makes sense because the delta will have to change a lot. Yeah, you have essentially the payoff is the derivative is discontinuous, so the second derivative is actually going to infinity near this point as it goes to expire. That in this model, gamma is not that relevant. No, gamma is still relevant in the discrete model. If you remember, if you take the limit, essentially you are getting the continuous model. So if you take enough periods, there is a chance you will have this gamma blow up problem, even in the discrete version. I mean, it's obviously not going to go to infinity, but it could get very big still. So. Like if you had 1,000 periods and each period is representing like an hour, theoretically the stock could be swinging around this strike price at the end of its life cycle for the last few hours or something, and it could go crazy. So even in the multi period model, you could still have that same gamma problem. Yeah. All right, I think I'm gonna end the recording here, but I'll still